Hello, good morning. Today we are going to go over thermochemistry in two short videos. You have already covered thermochemistry in the first semester, but let's be realistic, you might have forgotten, and this is really the foundation for the next unit, that's thermodynamic. So let's get started. So the first question we want to answer is, what is heat? You may think it's a relatively simple concept, but it's not, and proof that it's not is that it's been an elusive thing to explain for scholars and scientists for a very long time. In the 1600s, they had this theory that was called phlogiston. The word comes from the Greek word for heat and flames, and is actually used in some medical terms like phlogosis, that means the inflammation of a certain organ. And in this theory, heat was an element. So they were observing wood burning, and obviously you have a big pile of wood, and after you're done burning there is just a small pile of ashes, so something has gone away. And they had no concept of gas, they didn't know what gases were, so their explanation was that wood was sort of a compound made of ashes and phlogiston, and when you were burning it you were releasing the phlogiston in the air, and so you were subjectively perceiving the heat. And they were also using that to explain oxidation, so for example the rusting of a nail. So they had it completely opposite to what we understand now. So for them, iron was a compound of rust, they would call calx, and phlogiston. And when it was getting oxidized, you would release the phlogiston in the air, and you would be left with the element that in their mind was the rust. Now, of course, we know that rust is a compound. It's iron oxide, so it's a compound of iron and oxygen, while the metals, the iron is per se, the one we have in the nail, is the element, right? So, but you can't just dismiss it as stupid, as I've seen doing it on some website, because you need to remember what knowledge they had available. It's easy for us because we have the enormous advantage of relying on century and century of scientific progress. And so truly we can look so much ahead because we are dwarfs, but we're sitting on the shoulder of giants. That's all the science that's been done before us. So they use this theory also to kind of explain metallurgy. So the ore that they were finding in their mind were elements, and they were during the process of metal smelting, you would have to add back the phlogiston to get copper or iron or tin or whatever kind of material you were trying to extract. So this theory came to an end in the 1700s when they started discovering oxygen and carbon dioxide, although they were calling it differently, and also having accurate way of measuring weight. And so they would realize that when you're making an oxide, the mass is actually going up because you're adding oxygen. And this was made by Lavoisier, who was a French scientist, and he died in the French Revolution. He was executed with a guillotine. And in his mind, heat was a fluid. It was still sort of an element, but a sort of an odd one because he had no mass. He had a volume, but he had no mass. And it had no odor, no taste, it was invisible, and it was also self-repellent. So when you have a hot body and you leave it on the table, like a cup of tea, it would eventually get cold because these units that you could call caloric would just go away. And if you put two bodies at a different temperature in contact, the caloric would spontaneously flow from the hottest one to the coldest one. This theory is still so. And for example, when you observe dilation of objects because you're warming them up and the volume increases, like a piece of iron, that was because caloric was entering, and so having a volume was dilating, but not having mass, you would not observe an increase of weight. Now you may think that's kind of odd to think to something that has a volume but doesn't have a mass, but it was largely accepted because it was effective in explaining a bunch of things. So they were able to put together all the gas laws and even some initially concepts of thermodynamic by Sadi Carnot, that as we will see was kind of a central figure in the development of thermodynamics. So it was accepted for a long time. Bit of gossip: when Lavoisier died, his wife had to run away to England, where she ended up marrying Rumford, that was responsible for the dismissal of her late husband theory. So I don't know if it was because of that, but eventually they divorced, so that marriage didn't work well. So Rumford was the sustainer of a different theory. There was, instead of caloric, he was proposing a theory where heat was some form of movement, and this is pretty much what we do today. But as I said, the two theories kind of coexisted for a long time because, all in all, caloric was a good explanation. So people are typically reluctant to go for something more complicated if they don't have to. Rumford was in the business of making cannons, and to make a cannon you need to drill a hole in the main body of the cannon, and in doing so, of course, you generate a lot of friction, a lot of heat. So his observation was that the heat was enough to boil water, and the heat would never run out, so you would just keep going forever. And this is obviously kind of at odds with the hypothesis that you have a substance, because if you have a substance, eventually you have a finite amount and you would run out of it. So yeah, this is again just the bit of gossip. So what is heat? It is a form of energy that can be transferred between two bodies at different temperature. We do not say that a system contains heat. A system contains a lot of energy that basically of two kinds, kinetic and potential, and some of this energy may be transferred between bodies, and that's what heat is the energy that is transferred. One thing that tends to be kind of confused is the heat and temperature. Heat is a form of energy, while temperature it's the measure of the thermal condition of a body. For temperature we use units like kelvins, Celsius and Fahrenheit depending on the scales. We tend to use mostly Kelvin in science, and the temperature is proportional to the kinetic energy of the body when measuring Kelvin. So of course, if I measure the temperature in Celsius and I increase the temperature in Celsius, the kinetic energy is still increasing. The beauty of using Kelvin is that there is a direct proportionality. So for example, if I double the temperature in Kelvin, I can tell that the kinetic energy is also doubling. That means that if the temperature in Kelvin is 0, so absolute 0, the kinetic energy is also 0. So that's the only situation in which you would have no movement whatsoever. We are talking here of atomic movements, electron movements, molecule movements. Molecules are in constant motion by oscillating around their angles, around their the length of the bonds. So even if you're looking at a table and the table looks standing still, there is at a microscopic level, there is a lot of movement going on. And this movement ceased only when you are at 0 Kelvin. That is one of the reasons why conceptually we cannot go below 0, because we would have sort of a negative movement that doesn't really make sense. So there is a limit theoretically to how cold something could be, while there is no limit to how hot something could be. Heat is thermal energy that can be transferred from one body to another, and the units we use are joules. Very much used is also calories. There are two types of calories, and the main way they are indicated is with a small c or with a capital C. The capital C corresponds to kilocalories, so there will be 1,000 small calories in 1 big calories. The last one, is the one that you typically see listed in food packages. So an important concept in thermochemistry and thermodynamics is the concept of the system. The system is the part of the environment that we have decided to study. So there's going to be a boundaries clearly defining what's the system and what is not, and whatever is outside the system is the surrounding. And there is nothing else but system or surrounding. So something, any object should either be inside the system or in the surrounding. So the two together would give you the universe. So as you can see in this little GIF, you have a flask and there is some liquid in it, and there are bubbles. So if the flask is open, the flask is going to be our system, but obviously I have a gas that's coming out from the flask. So also, if whatever is in the system is hot, eventually it's going to get colder because heat is coming out. So I have here a system in which the boundaries are not very strict and are allowing things to go out or eventually in. So based on this, let's say, transfer of heat, we can classify the heat being transferred into positive or negative. So let's start with a simple example. You are trying to get fit for a sport event, and you're trying to keep a diary of your calories, and you would have you would spontaneously decide to assign a positive sign to all the food, so all the calorie intake through eating, and all the calories that you're burning by going to the gym or exercising or doing weights and such, those you would indicate those with a negative sign, and so you could keep a balance. So your body would be the system in this example, and we are calling everything that's getting into the system, the energy that's coming into the system, endothermic. And the energy that's coming out of the system is those processes are going to call those exothermic. The same applies if we substitute the human body with a test tube. All the heat getting into the test tube, for example, we are heating up with a Bunsen burner, is going to have a positive sign. That process is going to be endothermic. All the heat that's coming out of the test tube is going to have a negative sign, and that process is going to be called exothermic. Where you can get a little bit confused is because if you're holding the test tube, then and the process is, let's say, exothermic, that heat is coming into your hand, you're feeling a warm sensation, and in your mind, because you tend to be self-centered, right, so the heat is coming into you, and so you're tempted to say that that's endothermic. But the perspective, the point of view, should always be the inside of the test tube, the system, not you. An important classification of systems is based on the permeability of the boundaries, what can get in and out of the system from the surrounding or to the surrounding. So in this example, we have a pot that's on the stove and is boiling and is open. And we can see that steam is coming out. So if we don't, if we don't pay attention, we may run out of water eventually. So also heat is obviously coming out. If we turn off the stove, the water would go cold. So both energy and matter are able to cross the boundaries of the system. So we call this system open. If we put a lid, we can avoid the water from evaporate. We would still be losing heat. So we call this system closed because only energy can go through. The metal is a good conductor of heat, so eventually, if we don't keep providing heat, the pot would go cold. If we want, for example, if we have coffee and we want the coffee to stay warm for a long time, we need to use a coffee mug. And some fancy coffee mugs, they may keep your coffee warm for many hours, right? So in that case, nothing can go through, and we call that system isolated. Now, isolated system is sort of abstraction because even, if you think about coffee mug, there is really, even the fancier, eventually the coffee would go cold. So it's really hard to make a perfect insulation. But, for most of the application, we can just make approximation, and if we are fast enough, we can assume that our system is isolated. That's what we did in the lab when we used the coffee cup calorimeter in the first semester. So thermodynamic functions, that are those variables that we measure to describe the system. So for example, volume, pressure, temperature, energy, and we will define more in thermodynamics. Those are thermodynamic functions. They can be either extensive or intensive. Extensive properties depend on how much stuff you have, and they are additive. So if you take 100 milliliters of water and then another 100 milliliters of water and you put them together, you get 200 milliliters of water. So the volume depends on how much water you have. While, for example, the temperature, that would be intensive, because if you take 100 milliliters of water at 25 Celsius and you mix it with another 100 milliliters of water, and those are at, let's say, 75 Celsius, and you mix them, what's going to happen? There is heat transfer between the two, and they would settle halfway, so 50 Celsius. So the temperature is not going to be the sum of the two temperatures. In this case, it's going to be the average. So that's an example of an intensive property. So as we said, the energy of a system can be mostly categorized into two main types, kinetic and potential. The kinetic energy depends, you might have learned in physics that there is a relationship between the mass, the velocity of an object, and the kinetic energy. There is also another relationship that describes how kinetic energy vary is a function of temperature, and that K is the Boltzmann constant that's equal to the ratio between the gas constant and the Avogadro number. So it's kind of a neat relationship. You don't have really to worry about having to solve any problems that implies these two formulas. The only thing that you need to remember is that the kinetic energy is directly proportional to the temperature measured in Kelvin. So all these different types of energy that are in the system, collectively we call them internal energy, and that's it's indicated with the letter U. With the letter E, we indicate a different type of energy. That's the energy respect to the outside environment. So the internal energy is the energy due to this microscopic molecule movement. The potential energy, that's due to the fact that we have chemical bonds, and we know that breaking bonds could release this energy, intermolecular forces, and so forth. But if that, let's say, a sample of water is standing still on a lab bench, that's all there is. But if the glass of water is moving along the room or is getting at a different height, then there would be a different kind of energy that would be respect to the outside movement, and that's what is indicated by the letter A. So we will mostly be worrying about internal energy going on. We are never able to measure the absolute value just because they are so complicated and there are so many components into it. All we can measure is how they change from a certain instant, the initial state of the system, and what's the difference after a certain transformation happened. And these differences are conventionally calculated as final value minus initial value. So some function can be described as state function, while others are path function. So let's consider a simple example. Let's say from downtown Plato we want to walk all the way up to the M, right? And there are different ways we can do that. We can take a ride, we can take a hike, we can go by bike, I can take a taxi, bringing with them. I don't know if there is an actual road, but obviously there are certain things that would be the same. So for example, the difference in elevation between the top of the mound and the same Main Street is always going to be the same. So the change in potential energy does not depend on the way I go from the initial point to the final point, but the time that it's going to take me, the amount of calories that I'm going to burn if I'm trying to exercise, the money if I have to take a taxi, those are going to be different. So those are a function of path. So energy, for example, is a function of state. The change in internal energy does not depend on the path we take. It depends only on the initial and the final state. As I said, the difference is typically calculated as finals minus initial, and for function of state we use a capital letter. So internal energy, pressure, volume, temperature are function of state. The first law of thermodynamics is really a conservation law. So we know already that matter cannot be destroyed or created, and that's why we have to balance chemical equation. The same applies to energy. Energy can be converted from one form to another, but cannot be created or destroyed. So we can never think to be able to devise, to design a device that produces energy out of nowhere. That would be perpetual machine of the first order. That's deemed impossible by the first law of thermodynamics. So because energy cannot be created and the universe is an isolated system, as much as we know about it, the total amount of energy that is going to be a constant from the Big Bang all the way to now and to the foreseeable future. So the change in the internal energy of the universe is going to be zero. That means that but energy can still be transferred between the system and the surrounding, but whatever is coming out of the system needs to be accounted for in the surrounding. If the system is losing energy, that would be negative, then the surrounding is acquiring energy, that would be positive. So it would be the same number, just with a different sign. So for example, you are having a campfire. The system is the burning wood. That's an exothermic reaction that's giving off heat. That heat is not lost, it's just going into the system, making the air warmer, making you warmer, so you're the surrounding. And you're getting exactly the same amount of heat that the wood is losing. Okay, so this is a different way to write the first law of thermodynamics, in which we assume that whatever change in internal energy that the system is experiencing can be basically reconducted to two things: an exchange of heat and an exchange of work. Note that, so Q is the heat and W is the work, note that they are written with small letters, so they are not capitalized. That tells you immediately that they are not function of state. And we will see an example to show you that if you are not believing it. It's important that we agree upon convention for size. Now, convention just tell you that that's sort of an arbitrary decision, and we will see that there are different conventions. But in general, in chemistry, the approach that we use is that the perspective, the point of view, is the system. Whatever is increasing the energy of the system is positive. So that could be heat coming into the system. So for example, I'm putting my test tube over a Bunsen burner, or I'm performing a work on the system. So let's say my system is a cylinder and I'm compressing it. Imagine it's like compressing a spring, is like storing some energy that can be released afterward. Whatever is coming out of the system is negative. So it could be energy given off in an exothermic reaction, that's negative, or it could be work performed by the system onto the surroundings. So for example, in your car, once you have the combustion inside the piston and the cylinder expands, you are having work done to the surroundings, so the car moves ahead, but the system is losing energy because it's burning the gasoline, so it will have less gasoline that initially was there. Now, this is just summary, a schematic drawings that show you all this design convention, so there isn't really much more to say. Okay, so there are many different types of work, but the simplest that we will consider in chemistry is what is called pressure volume work. So it's the work performed by a piston that is moving inside a cylinder. So you can see the cylinder here, and you can have the piston going up or going down, and that corresponds to a compression, in which case it would be work performed on the system, or an expansion, in which case it would be the work performed by the system to the surrounding. So you have again a recap of the signs. So how do we calculate this? Why do we choose the PV work? Because it's simple to calculate, because the work can be calculated as the product between the pressure that's acting upon the piston times the change in volume that you are experiencing with the compression or the expansion, and that's going to be clear here. So the work can be calculated with the formula above, so it's minus P delta V. Now the minus sign that's in red can bother you, because oftentimes students think because the minus is in front of the P, that means that the pressure is negative. That is not the case. Pressure can only be positive, but delta V can be positive or negative depending on in which direction you are going, right? So let's consider our piston, and there is a change in volume, and the change in volume is this one, right? This is your change in volume. So let's imagine we are expanding, so we are going from left to right. If we are expanding, the final volume is going to be larger than the initial volume. Therefore, when we calculate the difference, it's going to be positive. If the difference is positive, when I multiply with the pressure, that is always positive, I'm going to get a positive. However, that's a problem, because I decided to use a convention in which the expansion, that is a work done by the system onto the surrounding, has to come up negative, and instead is coming up positive. So to fix the issue, I'm going to stick a minus in front of P delta V. So that minus has the only function of making things coming out as I want them, because of a specific convention that I have adopted. So this way the work is negative as I want it, and it corresponds in fact to energy lost by the system. Let's imagine we have instead a compression. Okay, so we're going from right to left. In this case, the final volume is going to be smaller than the initial volume. The change in volume is going to be negative. When I multiply by the pressure, that's always positive, it's going to stay negative, but it has to be positive, because a compression is a work done on the system is gaining energy. So again, my minus sign is going to do the trick, and is going to make things come out as I want them, that is positive. So if you don't believe that PV is a work, as a dimension of work, you can actually check for the units, and in fact you come up as a if you do some dimensional analysis, you come up with force times displacement. So at this point, all my biology people can go and get a coffee and take a pause, and then all my engineering people are going to stay here, because I have bad news for you. So there is a difference in the sign convention between chemistry and physically, and especially engineering classes. So I just don't want you to get to those classes and then think that I've been lying to you. So what happened is that the first law of thermodynamics is written differently. Instead of Q plus W, as in chemistry, the physicists write Q minus W. As a consequence, they have a opposite. Actually, that's the original reason why they have the different convention for the first law, is because they consider the work done by the system to be positive, differently from us. The reason is this difference is historical. Chemistry is centered into the perspective of the system. So what makes chemists make a decision about the sign is the system gaining or losing energy. From the engineering point of view, you're trying to build a machine, and so whatever work the machine system is performing towards the surrounding is positive, because it's something that you can make money out of it, basically. So that's why it's a difference of sign. Now, conventions are arbitrary, so one is as good as the other, as long as you are internally consistent, and that's why they had to change the formula. You come up with exactly the same results. Okay, So we can now all come back together to the next slide. Okay, so now that we're all back together, we can go back to the first law of thermodynamics. As I was saying initially, Q and W are not function of state, and that's why I wrote them with small letters. While while internal energy is a function of state, that's why the U is capitalized, right? So let's imagine for a moment that our chemical reaction happens at a constant volume. That means that the container is sealed, and that would be a bomb calorimeter, if you remember from first semester. In this case, the work would be zero, because if there is no change in volume, delta V is zero, so whatever is the pressure, W is equal to zero. And therefore, the variation of internal energy would be equal to the heat. So the heat exchange at constant volume, because it's equal to delta U, is going to be a function of state. But that's not the most, let's say, convenient thing to do in a lab. Often, if you remember, the vast majority of the reaction you will be performing, it was an open container. If the container is open, the pressure acting on the system is the same as you have in the surrounding, that is the barometric pressure, that is constant, and it's easy to measure with a barometer. So that's a more interesting setting, more practical, let's say, more easy to handle. So at constant pressure, the work is P delta V. It's easy to calculate because if P is a constant, it's a simple multiplication. It doesn't require calculus. In this case, being the volume a function of state and U a function of state, the heat exchange at constant pressure becomes also a function of state. And so it's really easy to measure, as I said, because all you need is a coffee cup calorimeter, basically. So we're going to give it a special name, that is H enthalpy. So the first law of thermodynamics can be written like that, just by substituting. And if you want, we can solve for delta H and get this. Okay, so delta H is the change in enthalpy of the system, that is the heat transfer in condition where the pressure is constant, and is a function of state. Although normally heat and work are not function of state unless we are acting at constant pressure or constant volume. So this is to show you that Q and W normally are not function of state. So if we have a certain amount of octane, that would be basically, in a simplification, what you burn in your car. We can transform it, we can burn it and transform it into CO2 and water and release with this a certain amount of energy. Now this could happen in a car where the energy is used at least partially to produce a work, because the car would move, although you know that there is always a certain amount of heat lost as heat, because by the end of your trip you put your hand on the frame of the car, you can see that it's warm. So there is both production of work and heat. If instead you're burning it in a container because you're trying to get warm, 100% of the energy would go into heat. And so obviously the amount of Q in the second scenario is much larger than the amount of Q in the first scenario. Also, you know that there are many different cars with many different mileage. So for some car, you get out more energy and you waste less, let's say, energy in heat, and you produce more work. While for a very old car, you would have a lot of heat and not much work. So there are infinite paths that you can think, all coming up with different value for Q and W. So now, this is the last slide. So we are done with the PowerPoint presentation, and I would like you to go and watch this movie that's a very clear explanation of latent heat. See you at the next